Swayam Prabha. Digital India. Educated India.
We are coming to a very famous machine learning model, namely the hidden Markov model. And as just before the connection dropped, I said that in part of speech tagging also we are faced with the problem of ambiguity resolution. And this was illustrated by many examples. The example that we chose in particular was clause, which can be adverb, verb, noun, adjective, everything. So from the context, we have to find out which part of speech tag applies to this particular situation. By the way, what is being presented is English centric, and this mapping of word to part of speech, that mapping or binding of word and part of speech is very loose in English, very loose. Okay, in English, almost every noun can act as a verb. Almost every noun can act as a verb. This is not true, for example, in other languages. In Hindi, for example, the word billi or the word kutta, they are not, they can never function as a verb. Okay, paid, for example, is a Hindi word. Gach is the Bengali corresponding word. They never function as verb. But in English, tree can function as a verb. Dog functions as a verb. Okay, misfortune kept dogging John. Dog means to follow. Okay, so there is a very peculiar situation about English. So you might think that the part of speech tagging problem would be easier in other languages compared to English. This is true. This is true. Okay, this is true. And there is another interesting phenomenon. It's called verbalization. Verbalization, converting a noun to a verb. So a beautiful example comes from Sanskrit. In Sanskrit, the word for tree is drum, briksha, drum, and so on, drum. So drumayate behaves like a tree is the verbal form from drum. And what we have applied on this is derivational morphology. A noun has been converted to verb by what is called derivational morphology. The Sanskrit term for this is tadhit prayog. The pratyay, or the morphological process which is being applied there is tadhit prayog. Okay, drumayate behaves like a tree, but drum or bricks, they never function as a verb. Okay, so therefore the ambiguity question for part of speech tagging differs from language to language, and we would say, to be a little more technical, that the part of speech tagging situation has higher entropy for English. Okay, it has higher entropy for English than other languages, definitely Sanskrit, and definitely many of the Indian languages. So if you exclude the possibility of a word to be a verb while it is a noun, then you are solving a tremendous amount of problem for part of speech tagging for that language. Okay, so English has that peculiarity. And recall that in the beginning of the NLP lecture, I said that algorithms have been designed for English in NLP over many years because of richness of data availability in English, but that picture may not hold for all languages. Okay, so we come to the technique that we are applying for part of speech tagging, namely hidden Markov model. And which axis in this three-dimensional diagram we are referring to? The axis is the algorithm axis or the technique axis. We have understood, we have decided on the language, English. We have decided on the problem, part of speech tagging. Now we are going into a detailed discussion on the technique. But we'll always, transit between technique and the problem, that is hidden Markov model and the part of speech tagging task. So this transition will go on happening. Also, since the whole session is being recorded, I would prefer that if you ask your questions in the chat box, I will devote 15 minutes towards the end of this lecture, 15 minutes, okay, which is quite a lot of time for answering all the questions. So kindly put all your questions without any hesitation, any question that comes to your mind at the chat box. And we are storing all these questions, many of which are very valuable. Okay, so hidden Markov model is illustrated traditionally, okay, in textbooks in a very famous paper by Rabiner, R-A-B-I-N-E-R, Rabiner, through this example. Okay, and I hope my slide is transiting. The slide title is A Motivating Example. Can one of you say that this is the slide on the screen?
Yes, that
Yes,
is the
sir.
slide. Yes.
Okay, great. Okay, so there are three arms or three bowls, you can say, which have red, green, and blue balls, and you can see the numbers on the screen. In each arm, we have 100 balls, but the color distribution is different from one arm to the other. In the first arm, we have 30, 50, and 20 distribution, red, green, and blue. The RGB distribution in arm 2 is 10, 40, 50. In arm 3, 60, 10, 30. So you can see that if you pick a ball with replacement, then the parameter, the probability of red ball conditioned on arm 1, given that the arm 1 is chosen, is 0.3, 30 by 100. Same probability is 0.1 for arm 2, 0.6 for arm 3. All right. So with replacement, we have this constant probability of red ball, green ball, blue ball given the arm. Okay. And then there is another probability of transiting from one arm to another. So one of these arms is a special arm, in the sense that we start from that arm. But there is nothing sacrosanct about a particular arm being the starting arm. Okay, arm means a bowl. So I could start from arm 1 or 2 or 3, but then the next arm that is chosen is decided by a probability. Okay, it is decided by a probability. So if I begin with arm 1, then I have the choice of coming back to arm 1, okay, after picking a ball, picking again from arm 1, or going to arm 2 and picking a ball, or going to arm 3 and picking a ball. So you can clearly see that there are two probabilities involved, two obvious probabilities involved. One is picking a ball given the arm, and the other probability is next arm given the current arm. Which arm do I choose next? Okay, so the random variable of choosing the next arm is controlled by what is called transition probability, arm I to arm J, and the random variable of which ball comes out from that arm is decided by what is called the observation probability or emission probability. Okay, so picking a ball given the arm and the next arm given the current arm, these two are the predominant probabilities. But I also said that which arm you begin to start your operation from, that also can be decided by a random variable. This is called the initial probability. Which arn is my starting arn? Okay, so this gives you a complete picture of what is happening. A very elegant and simple situation. Okay, but what is the question? Why all this? What is the question? What is the problem statement? The problem statement is that we are given a sequence of balls which have been picked with replacement. Sequence of balls is presented. You have to predict the best possible arn sequence. Okay, you have to predict the best possible arn sequence given this ball sequence. What is the probability of this sequence coming from a particular sequence of arns? So it becomes a question of probability for a particular position. So if I have an n ball sequence, okay, RR, GG, BR, GR, red, red, green, green, blue, red, green, red. If this is the sequence, I want to know which arn did R come from, then the next R, then the next G, and so on. What is the sequence of arns from which these balls came, one after the other? Okay, is the question clear? I think the question is clear. The input to the problem solving block is a sequence of observations, namely the balls, and the output is the state sequence where each state means the arm. Not very different, in fact very almost identical to the question of asking, if I have seen these words, what is the best possible tag sequence corresponding to these words, where each tag is looked upon as a state. So you see, this is the mapping that Jelinek and team did. They asked, what if I look upon the ball sequence as the word sequence and the arn sequence as the state sequence, namely the tag sequence. This is the mapping. Now on hindsight, it seems like a very simple task. It was not so when this was done. This was a stroke of genius. So this was a disruption or a paradigm shift which happened in natural language processing. It ushered in data-driven machine learning model for part of speech tagging. And this is how disruption happens. And in AI, ML, NLP, CV, speech, disruption happens by data. Okay. Another disruption which has happened in recent times, maybe about 7, 8, 10 years old, I would say, is the introduction of word vector. Okay. Word embedding and deep learning. So words are represented as points in a geometric space. Imagine, okay, words are becoming points in a geometric space, and these points are vectors obtained by training a deep neural network. Not really very deep. Input layer, hidden layer, and output layer. Okay, so this is another disruption. And how did it happen? It happened because Google had an enormous amount of corpus, and for every word there was an enormous amount of context. So why not, somebody sat down and said, why not exploit this? And there was, of course, prior work done by Bengio, Hinton, and the person from Facebook now. Okay, all three of them got Turing Award this year, Turing Award last year, because of this contribution, looking upon words as vectors and obtaining those vectors by training. Okay, so I'm digressing a bit, but just to make you aware of the perspective, the way the disruption happens when science and technology moves forward. Okay, so this was a disruption to think that emission probability and state transition probability and the hidden Markov model and the decoding algorithm from the hidden Markov model could be gainfully used for doing part of speech tagging, and later for any sequence leveling task. So this was a very convenient situation because NLP is processing of sentences, and sentences are sequence of words. So here, from the data that is given to us, the number of balls within the urns, and the fact that there are 3 urns, we have what is called the emission probability table. You see the probability of red ball from urn number 1 is 0.3, green ball 0.5, blue ball 0.2. This is as per the data given to me. Similarly, U2 and U3, the row probabilities give me these values. What do the column probabilities give? Do they give anything meaningful? I leave it as an exercise for you to think. Okay, do the column probabilities give anything? So this 0.3 is probability of R given U1. 0.5 is probability of G given U1. Okay, so this is the meaning of every cell. So when I add the row probabilities, they must add to 1. You must pick some ball from U1. When I add the column probabilities, they also happen to be 1. But is this a coincidence or is it something to be expected? So I leave it as an exercise. I would request the TA team to note down this exercise. All the exercises, assignments, projects should be up on the web, as well as the 3 platforms of communication that we have. Okay, so the question is, the column, does the sum of column probabilities in the emission probability table mean something? Similarly for the transition probability table. So let me just repeat the assignment. In a hidden Markov model, given the transition probability table and the emission probability table, the rows sum to 1. Should the columns also sum to 1? If yes, why? If not, why not? Okay, this is the question. Please put it up on the web as well as the 3 platforms. And I request the class to think about it. Okay, so similarly, if I look at the transition probability table, then again I have conditional probabilities. Okay, 0.1 is probability of U1 given U1. This is the probability of remaining in U1 having picked a ball from U1. The next cell, 0.4, is probability of U2 given U1. The probability of transiting to urn number 2 from urn number 1 and choosing the next ball from urn number 2. So this is the way the transition probability table and the emission probability tables are given. Okay, then you also have an initial probability, which is a row vector or column vector, which gives the probability of choosing U1, U2 or U3 as the starting urn. And remember, this is the question we are trying to solve. Given the ball sequence, predict the best possible urn sequence. So this can be represented diagrammatically. That means the hidden Markov model itself can be represented diagrammatically with 3 nodes, U1, U2 and U3, and from each node 3 arrows, 3 black arrows marked as R, G and B. So U1, from U1 we see R, G and B arrows coming out with 0.3, 0.5 and 0.2. That's because 30% of the balls are red, 50% green, 20% blue. And we also have a blue arrow coming back to U1. There is nothing but probability of U1 given U1. The probability of coming back to U1 starting from U1. That probability is 0.1. The probability of going to U2 from U1 is 0.4. From U1 to U3 is 0.5. Now 0.5 plus 0.4 plus 0.1, this must add up to 1. From the current urn, I should be in one of the 3 urns. So that's why they must add up to 1. Okay. And the emission probabilities, which are shown by black lines, they also should sum up to 1. So this is a very convenient and elegant representation of a hidden Markov model. In the hidden Markov model, the states are represented as nodes or circles, and there are arrows going from one node to another representing state transition, and there are arrows with emission random variables values and the corresponding probabilities. Okay, so this is the diagrammatic representation of three things, namely the transition table, the emission probability table, the transition probability table, and the machine, whole hidden Markov model itself. So now another interesting thing happens. You can show by means of probabilistic algebra, by applying rules of probability, that you can multiply the emission probability with the transition probability and convert all these arrows into just 3 transitions. Okay, if you had transition probability, then you need one arrow to come to U1 and the 3 arrows for the 3 emissions R, G and B. But it turns out that you can multiply the transition probability with the emission probability and just reduce these 4 arrows to 3 arrows, okay, and all of them coming back to U1. So you can say R on R, you have the probability of 0.03. So this is a joint probability. Probability of remaining in U1 and emitting R together given U1 is 0.03. Similarly, probability of remaining in U1 and emitting green is 0.05. For B, it is 0.02. This is nothing but product of transition probability and emission probability. And you will be legitimate in asking, how can you take the product? Okay, how can you take the product? So we'll see that very soon. Similarly, when you go from U1 to U2, you had values of probability as 0.8, 0.2 and 0.12. Is it? Just a minute. You had probability values as 0.4. U1 to U2, it would be 0.4. Okay, and then you have these R, G and B as the emission, R, G and B as the emission. Then 0.3 into 0.4 will be 0.12. 0.3 into 0.5 will be 0.4 into 0.5 will be 0.2. 0.4 into 0.2 will be 0.08. Okay, so I can again multiply U1 to U2 transition probability with the emission probability from U1 and convert this U1 to U2 transition as a joint probability situation. So you see we have here 0.02, which is 0.4 into 0.2, G is 0.2, 0.4 into 0.5 and B is 0.12, 0.4 into 0.3. So I can always multiply transition probability with emission probability and see the target state and the emission. Okay, so this particular point may be little complex, the fact that you can multiply the two probabilities, but actually this is giving you a joint probability. Then the diagram becomes simpler. Now, given this hidden Markov model, which is nothing but a finite state automaton with probability values, we can solve a number of problems, but 3 problems are classic. They are absolutely fundamental to hidden Markov model. Probably the most useful task that is performed by hidden Markov model is this. Given the observation sequence, find the possible state sequence. Okay, this is the most useful application of hidden Markov model. This this task is also called the decoding task. Decoding task. You will hear decoding in other statistical machine learning situations as well as deep learning situation. Especially when you use BiLSTM, RNN, etc., then the output is obtained by decoding. Okay, so this is executed by a very famous algorithm called Viterbi algorithm. The next question is, given the observation sequence, find its probability. Again, a very famous algorithm called forward-backward algorithm, and forward or backward algorithm. And the third question is, given the observation sequence, find the HMM parameters. And the parameters are nothing but transition probabilities and emission probabilities. Okay, so these are the three questions. And these three questions have extremely useful many applications. So the first question gives you a way of solving part of speech tagging. It gives a way of solving named entity recognition, words and disambiguation, any kind of sequence leveling task. The second question gives you the probability of a sequence of entities. In particular, if the sequence of entities is sequence of words, then this solves what is called the language modeling problem. What is the probability of a sequence of words? So that has tremendous amount of application in machine translation, in natural language generation, in question generation, any kind of situation where a sequence of textual segments have to be produced. And the third question is indeed the learning question, where you are getting the parameters of the hidden Markov model, which define the hidden Markov model from the data. Okay, so this is the set of three questions which are classic problems with respect to hidden Markov model. Now let me just ask you, is the slide in front of you on the screen reading classic problems with respect to HMM? Are you seeing this slide? Yes, sir. Yeah, okay, okay. So Viterbi algorithm. Yeah, any question?
Yeah, like the are the probability, right?
Are the probability values, transition and emission probability values.
So 2 and 3 are the same problem?
No, in 2 we are asking what is the probability of the observation sequence. In 3, given the observation sequences, and that finite state probabilistic automaton goes to an accepting state, we are asking what are the parameters of the hidden Markov model. This is called the Baum-Welch algorithm.
So can you repeat that? I didn't understand.
So you are given many sequences of observation which lead the hidden Markov model to an accepting state. Then from those sequences you want to find out the transition probability and the observation or emission probability. In second question, all these probability values are given. You want to find out the probability of the whole sequence. In the third question, only the observation sequences are given. No probability value is given. You have to infer it from the data. Okay?
Okay, sir.
Yeah.